Till now we have considered torsional vibration in great detail. Now we will be extending the method which we developed in the torsional vibration for the transverse vibration also, because transverse vibration is very important in rotating machinery, which occurs frequently because of the inherent fault which is there in the system, such as unbalance or misalignment, etc. In the previous lectures, we considered some of the transverse vibration, but for simple cases, like we considered single mass rotor supported on maybe rigid bearing or flexible bearing, and even we considered more complexity in the rotor in the form of gyroscopic effect, but all such analysis were very simple for single mass rotor system. Now, based on the experience of the torsional vibration in the previous lectures, we will now analyze the transverse vibration also for multi-mass rotor system, so that we can able to apply these methods for a real system. Now, let us see what are the things we will be covering. So, apart from the methods which we covered in the previous cases for torsional vibration, one important method, the influence coefficient method, which we will be covering for transverse vibration, and both free and forced vibration can be analyzed using this particular method. Basic concepts which we will be requiring for this is principle of superposition. Basically we will be dealing with the linear system, so this principle of superposition can be applied there. Influence coefficients, we will see the concept of this in more detail, so that even for larger system we can able to calculate the influence coefficient. Now let us see the influence coefficient method, how it can be applied to the rotating machinery. So, initially we will take very simple concepts of the this influence coefficient for static case, and then we will extend that for the dynamic case. So, if we have a flexible shaft, let us say massless shaft is there, and in this number of discs are mounted, or we can have n number of discs, shown here only 3 discs, and let us say some support conditions are there. In this particular case, let us say this is simply supported, but any other boundary condition or end condition can be there. Now, if a static force, if we are applying, let us say these are disc 1, 2, 3, if we are applying a static force to disc 1, because of this force, the displacement at disc 1 location, let us say that is x1, will be proportional to the force applied. So, if we increase the force in the same proportion, this particular displacement will increase. We are assuming that force we are applying gives the displacement which is small, and the force and displacement relations are linear, and this proportional, if we remove it, we will get a proportionality constant. So, x1 is, let us say, equal to some constant alpha 11 into f. So, this particular force we applied at location 1, and there itself we are obtaining the displacement. Now, in second case, if we remove this force here from this and apply the force, the same force in the second disc, and now this force not only gives the displacement at location 2, but also at disc 1 and disc 3, because the whole shaft will get deflected and we will be having displacement at 1 also. So, for this case, again, if we want to see the displacement at the same first disk location because of this force, that will be proportional to the force. If we increase the force, the displacement we expect will be linearly varying with that. And this proportionality, if we remove it, we will get another constant, and that constant I am representing as alpha 1 2 into f. So, this particular alpha 1 2, which is a constant, is representing that the first subscript 1 is giving us the displacement location, and the second subscript is representing the force location. So, you can see we are applying the force at second, and we are seeing the displacement due to that at x at disk 1. So, I have represented like this, and if we have similarly n number of disks, let us say n number of disks are there, and this is the nth disk, and if we are applying the force now at nth disk, so we expect the displacement due to this force, which is at the nth disk, at disk 1 displacement will be again proportional to the force, and we will be having a different proportionality constant alpha 1 n into f. Now, we can able to see that there is another constant, because the location of the force is different now and displacement is different now. And if we have a system in which, let us say, we are applying F1 force here, F2 force here, and Fn force here. So, we have n number of forces, we have applied n forces in all of the disk. Now, if you want displacement at disk 1, so that we can expect that there will be summation of this, only thing we will be replacing this f's with different forces. So, that means displacement at x will be summation of displacement due to force F1, that will be given by this one, then displacement due to F2 at the same x location. So, that will be F1 to F2 and so on up to nth force. So, we got force displacement at disk 1 due to various forces at various disk location from 1 to n. Now, the same concept we can able to extend for obtaining the displacement at disk 2. So, that we can able to write as, if we want the displacement at disk 2, so this will be alpha 2 1 F1 plus alpha 2 2 F2 and so on alpha 2 n Fn. These constants are now different, they are not same as the previous ones. Now, subscripts have changed. So, here you can able to see in these all constants we have first subscript as 2, which is representing that we are interested in obtaining the displacement at this location 2, and the second subscript is representing what are the forces at various disk locations, like here 1, 2, so force 2, n, so force n. So, this displacements we can able to extend for all the disk. Let us say for nth disk we will be having this relation and so on, f alpha nn into fn, and we can able to see these are all different. In general, we will see that in this particular case the influence coefficients will be having this property, cross couple terms will be same, and we can able to obtain this by usual deflection relations of the bending of beam, which we have studied in the strength of material. So, let us see the definition of the influence coefficient alpha ij. So, this particular quantity is the displacement at ith location due to force at jth location and when we are keeping forces at all other location, that is let us say I is equal to 0 when I is not equal to j. So, only force j is acting. So, what is the displacement at ith location is given by this, and all other forces we need to equate it to 0. So, this is the definition of the influence coefficient. Now, these equations which we have developed better now, because they are becoming larger in size, we can able to put them in a matrix form or like this. So, you can able to see that the first equation which we derive is this one. If we expand this, x1 will be equal to alpha 11 f1 alpha 12 into f2 etc. up to alpha 1n into fn. So, this is the first equation we derived, second equation and nth equation. So, this we have kept in a matrix form, and these are the various displacement vector. This is various force vector, and this matrix which in the compact form we are writing alpha matrix is the influence coefficient matrix. Influence coefficient matrix. And this particular in this particular case, what we assume that the force is giving only the linear displacement, but in transverse vibration we know that if we are applying a force in a simply supported beam, if we are applying some force, not only it gives the linear displacement, let us say at this location this is the x1, but also it gives the slope, because originally slope was 0, but now the slope has changed. So, some angle. So, the force not only gives the linear displacement, but also the angular displacement simultaneously. Similarly, if we apply only moment, that will not only give the linear displacement, but also it will give the rotational displacement or angular displacement. This is the transverse displacement. This is different as compared to the torsional one. In this particular plane only, we are talking about the slope of the elastic line of the shaft. So, basically when we are applying force, both displacements and angular displacements are taking place. So, the previous analysis we can able to extend like this. So, instead of the displacement only the linear, we can add the angular displacements. Also in the force vector, instead of only the forces, we can add the moment. And now, because the size of these vectors are 2n into 1, so influence coefficient matrix which was originally here, it was n into n, now it will become 2n into 2n. Now, additionally more influence coefficients will come corresponding to a moment and angular displacements. Now, you can able to see, if we want to expand the first equation, the linear displacement is caused by not only the forces which was originally was there. So, the first n these influence coefficients are related with the force, and this linear displacement is caused by the moment also. So, remaining n equation or n terms of the influence coefficients will be multiplied by this moment to give the linear displacement. So, you can able to see now the linear displacement is caused by forces as well as moment. Similarly, if we take the angular displacement, it will caused by the not only by the moment, but also by the force. Basically, they are coupled. So, this is a more general form of the this influence coefficient, in which we have considered both linear and angular displacement and moment and the forces. Now, whatever the analysis we considered previously, that was for static case. The forces which we applied was static force. Now, we will extend this particular case for the dynamic case. So, for the dynamic case, the forces will be time dependent, like unbalanced force, and now we will see how we can able to apply this influence coefficient method for the time dependent forces. So, this is basically a free body diagram of a disk. In this several forces and moments are acting, but let me first introduce the alpha 1 F1 prime. F1 prime, this is the external force which is acting on the disk. This is the external force, this is time dependent. So, basically now all the forces are time dependent. Similarly, we have moment which is external moment, time dependent. This may come if disk is not perfectly perpendicular to the shaft. If it is slightly tilted, so this kind of external moment may come onto the shaft, onto the disk, because of the tilt of the disk. So, M1 prime and F1 prime are the external forces. Now, because this is the free body diagram of the disk, disk was here, we have removed the disk from the shaft and we have drawn the free body diagram. So, obviously, at the hub of the disk will be having reaction force from the shaft F1, which will be there at the force at the on the shaft also, and also the moment. Moment will also be acting. So, basically this is the reaction moment and this is the M1 prime external torque. So, this is the external torque, external force, and reaction force and reaction moment from the shaft. So, this is the reaction moments which is coming onto the shaft from the disk. Now, let us take the positive direction of the displacement in downward direction. So, we will be having inertia of the disk in the upward direction, which will be opposite to the motion direction. Similarly, we will be having a rotary inertia term, which will be opposite to the tilting of the disk. So, tilting is in this particular case is clockwise. So, this inertia will be acting in the counterclockwise direction. So, I think I have defined all the forces. These are the external forces and these are the internal or reaction moments. Now, if we write the force balance. So, this is the external torque which is acting in the positive direction of x, reaction external torque, then reaction torque which is opposite to the motion direction is downward, reaction torque is force is in the upward direction. These two forces are acting on this disk should be equal to m1 into acceleration, linear acceleration. So, this is the force balance of this disk. Now, let us take the moment balance. This is the external moment, reaction moment from shaft. These are the two moment acting should be equal to the rotary inertia. So, this is the moment balance and this is the force balance of this free body diagram of the disk. Now, we can able to obtain free body diagram of the disk 2, 3 and all other disks. So, we can able to see corresponding to the second disk we have external force, reaction force should be equal to inertia. Similarly, external moment and reaction moment should be equal to inertia of the second disk. So, this is ID1, here ID2 and we can able to extend this for nth disk like this, where Mn is the mass of the nth disk, and Idn will be the diametral mass moment of inertia of the nth disk. These are all diametral mass moment of inertia, and this is the angular displacement and time derivative. So, angular acceleration of the nth disk. Now, for harmonic motion, because either due to the unbalance or if we are analyzing the free vibration, the harmonic motion can be represented like this, where omega is the frequency. For forced vibration, it will be the, like for unbalance, it will be the speed of the shaft, or if we are analyzing the free vibration, this omega will be the natural frequency of the system. So, this equations are valid. This we can able to substitute in these terms. Okay. Basically, now these equations we can able to put in a matrix form like this. So, you can able to see we have this is the displacement x1, x2, all angular displacements. These are the influence coefficient which we obtained earlier. This was the reaction force and moment from the onto the shaft. So, this equation we derived earlier for static case like this. So, D is equal to alpha F. F is the reaction force onto the disc onto the shaft. So, from these equations we can able to solve for F1 and F1, F2, Fn, M1, M2, Mn, and we can able to substitute in that vector, and we have done this here. Even we have considered the harmonic motion. So, omega square terms are also coming. So, you can able to see now. Earlier it was static force, now because of dynamic force we have these terms got changed. Now, this equation we can able to split in two parts, this particular vector. One is only the force and moment, so that is this one, plus omega square is common, and this vector. So, m1, x1, all these vector are cos. So, basically I have split this in two parts, and then I have expanded. So, because alpha matrix was common, so it will be multiplied to both the terms. Now, here alpha prime is this forces and moment, which is external torque and external force and moment, which is coming from the, for example, unbalance. Now, the second term, this term. So, what I am doing, I am multiplying these masses inside the influence coefficient, and I am only keeping the displacements here. So, that particular term is, so first two terms are, first term is same as previous one, only thing here, only the displacement I am keeping here, but mass terms I have included in the influence coefficient matrix. So, you can able to see those mass terms and diametral mass moment of inertia terms are now inside the matrix. This you can able to see now. Here we have D displacement vector, here displacement vector, they can be combined. So, what I am doing, I am putting this particular D vector in the other side. So, and this can be multiplied by identity matrix. So, this is the that one. So, you can able to see A is this matrix, D is common, and I have multiplied by I have divided throughout the expression by 1 by omega square. So, this 1 by omega square term is coming here, also here, and this is in the other side. So, minus 1 by omega square alpha into F. This is the external force term, external force and moment term. This is the displacement vector, and alpha is the influence coefficient matrix, and A is this matrix which contain not only the influence coefficient terms, but also the masses. Now, this particular equation is the required form of the equation. You can able to see, if we want the forced vibration to be solved, if we know the what is the force, external force in the system, we can able to get the displacement by inverting this matrix. So, we can able to see that D, we can able to get displacement as R into F prime, where R is the inverse of this, basically inverted this matrix to get the D. So, here D is 1 minus omega square, inverse of this whole term, omega square will be the spin speed for this case, inverse of this into alpha into F prime. So, this particular equation is this one, which is written in more compact form, and this A matrix is given by this. So, this for various angular speed, if we know the force values, we can able to get the displacement, and this is the force vibration case. Now, if we want to analyze the free vibration, so obviously we need to keep the external force equal to 0. So, this whole term will be 0. So, we will get this equal to 0, that is this one. So, this is for the free vibration. So, if we want the natural frequency of the system or the critical speed of the system, we can able to use this expression, where A is given by this expression, I is the identity matrix, this is the natural frequency. Now, omega will be natural frequency for free vibration, and because this is a homogeneous equation, we need to have determinant of this equal to 0, that will give us the characteristic equation, or as we have done earlier, the eigenvalue of the A matrix will give us the natural frequency, and the mode shapes will be given by the eigenvector of A. Now, we have seen the basic concept of the influence coefficient method. With this method, not only we can able to analyze the free vibration, also the forced vibration. Now, through some simple example, we will see how this method can be applied to obtain the natural frequency of the rotor system or critical speed of the rotor system. So, for this particular case, very simple rotor like this we have considered. This is simply supported rotor system. Mass of the shaft we are not considering, only the inertia of the shaft is there, and we are considering both mass and diametral mass moment of inertia of the disc. Now, various property of this are given here. Mass is 10 kg, ID is 0.02 kg meter square. Disc location is also given, that from right support it is 0.25 meter, and total length of the shaft is 1 meter. Diameter of the shaft is 10 millimeter. Young's modulus is given. So, and in this particular case, we are considering only the single plane motion, because as such this influence coefficient, they do not couple the vertical motion and the horizontal motion. So, single plane motion can be considered. So, now for this particular case, the displacement linear and angular are related with the force and moment with such influence coefficients. So, this influence coefficient we can able to get from any strength of material book. So, you can able to see that definition of the influence coefficient 1 is nothing but, we can able to expand this. So, alpha 1 is nothing but displacement, linear displacement of the disc for a force F y, keeping the moment equal to 0. So, basically alpha 1 is nothing but linear displacement divided by the force at the same location. Similarly, if we want to obtain the alpha 12, so that will be the linear displacement due to only moment when it is present in the system. So, we need to keep the force 0 in the second case, this 0, only moment is applied. So, whatever the linear displacement take place at the same location will be given by that displacement divided by the moment will give us the influence coefficient 1 alpha 1 2, and I already mentioned alpha 2 1 will be same as this one, and definition of alpha 2 1 is different. So, that is nothing but the angular displacement due to force at this disk location when we are keeping the moment 0. So, alpha 2 1 is angular displacement due to the force. So, definition is different, but the values will be same for both the case alpha 1 2 and alpha 2 1. And from any strength of material book we can able to get such influence coefficient relations, or we can able to derive also using this basic concept. Just we need to obtain the linear displacement and angular displacement corresponding to either force or moment, and that will give us the influence coefficient. So, for this particular case in which we have a Jeffcott rotor with offset disk where A and B are given like this, alpha 1 1, alpha 1 2, alpha 2 1 all are expressed in terms of the location of the force, geometry of the shaft and material property of the shaft. So, once we know all this property, we can able to calculate the influence coefficients. And for free vibration, we had this kind of relation earlier, which we derived, and for because now we have only two terms in the A matrix. So, this A matrix will be having the form of alpha 1 1 m, this we had earlier, alpha 1 2 I d, alpha 2 1 m, alpha 2 2 I d. So, if we substitute this here and then club this 2, we will get this matrix. Now, because it is homogeneous equation, determinant of this will give us the characteristic equation. You can able to see there is a quadratic in natural frequency square. So, we expect 2 roots out of this, and for various values of the data given in the problem, these are the influence coefficient values. So, if we substitute that in the previous polynomial, we will get the polynomial of this form, and we can able to get the roots, the solution of these two. So, this is the first natural frequency and this is the second natural frequency of the system. So, you can able to see that once we know the influence coefficient, it is quite straightforward to obtain the natural frequency of the system. Now, the same problem if we have disk at the center, because in the previous case we had the disk at the slightly offset position. If disk at the center, what will happen? The tilting of the disk will not take place if we are applying the force at the middle, because slope is 0. So, that means this coupling terms will be 0, because if we are applying force, only linear displacement will take place, and if we are applying moment, only angular displacement will take place at the middle. So, this coupling terms will be 0, and influence coefficients or these values will be alpha 1 1 and alpha 2 2 will be these. And now, we can able to see that the natural frequency will be given by this, because now there is no coupling terms. So, this equation will get simplified, these terms will be 0. So, this equal to 0 and this equal to 0 will be giving us 2 natural frequency, and these are the 2 natural frequency. So, now for when disk is at the middle, we are getting 22.244 radians per second as one natural frequency and 248.697 as second natural frequency, and these are different as compared to the previous one in which coupling was there. So, 29.4 and 290.4. So, even if we are changing the disk location, we expect change in the natural frequency. This particular example which we considered was very simple, but it was good in clearing the concept of the influence coefficient and how we can able to get the characteristic equation to get the natural frequency was quite clear. Now, we will take up a more complex example in which now instead of one disc, we have two discs in the shaft system, and this is a cantilever rotor system. In this particular case, for simplicity, we are considering only the force and the linear displacement. So, we are ignoring the moment and the that is the angular displacement. So, let us see how we can able to analyze this system. So, we have a rotor system like this in which we have two discs, mass of the shaft we are not considering, and we are considering that the disc is having mainly the up and down tilting motion, linear motion. Tilting motion we are ignoring it, and various property of the shaft and disc locations are given here, like diameter of the shaft is given, disc various geometries are given, mass of the disc first is 2 kg and second is 5 kg, and the diametral mass of moment of inertia of the disc we are ignoring it. So, for this particular case, we are first deriving the influence coefficient just for illustration purpose. So, basically we have two forces Fy1 here, Fy2 here, and this is the distance between the force and this is the L. Now, we can able to obtain the z axis is from here. So, we are measuring from this end. So, by bending moment concept we can able to obtain the influence coefficient. So, first we are obtaining the strain energy. So, for that we are obtaining the bending moment. So, for first segment from 0 to A, this is the free body diagram, this is the bending moment and shear force. So, if we take the balance, this is the bending moment for the first shaft segment. Similarly, we can able to get for the second. So, in this particular case Z is varying from 0 to L, and from A to Z is varying from A to L. So, for this case the bending moment will be given by this expression. This is standard procedure in the strength of material, and now we can able to get the strain energy of the system by integrating from 0 to A and from A to L, and once we have strain energy we can able to get the displacement. Let us say if we want the displacement at the force one location, we need to differentiate with respect to that force using Castiglione theorem. We will get the displacement at one location. So, we can put the expression of this bending moment, and we can able to get the displacement at location 1 due to force 1. So, if we simplify this is simple strength of material steps. So, finally, we will get the displacement. You can see because there are two forces, the strain energy is due to both the forces. Okay. So, the displacement at one location will be not only due to force 1, due to force 2 also, and this expression we can able to write it as y1 is equal to alpha y1 f1, that is we can say alpha 1 1, this is alpha 1 2. So, this is the alpha 1 1 and alpha 1 2 for this present problem. Similarly, so if we put the values of various property of the shaft, we can able to get this influence coefficient alpha 1 1 and alpha 1 2 from the previous expression. Similarly, if we want the displacement at y 2 because of the force 2, we can able to once we differentiate this, we can able to get the expression for y 2, and the term within this bracket will be alpha 2 1 and this will be alpha 2 2, and if we substitute the values again, we can get these influence coefficients also. A more systematic way of obtaining this influence coefficient by tabular method. Now, I am explaining because this can be extended for multi rotor system also. So, for we have formula for such cantilever system in which let us say Z is measured from here, A is the position of the force, total length of the shaft is L. So, the displacement at force displacement at any location can be given by this expression, and this particular expression is valid for 0 to A. So, between this range this particular displacement relation is valid. Second expression is valid for from A to L, because there is no force here. So, we expect a linear variation of the displacement here. So, you can able to see this is a linear variation of the displacement at that location. So, now these two equation which is generally available in the table in the strength of material book can be used to obtain influence coefficient which we obtained earlier. So, let us see how it can be done. So, two forces are acting. The first force distance from the fixed end is L1. This between two forces the distance is let us say L2, total length is L. Now, if we want alpha 11, for alpha 11 that means we have force acting here, this is the Z location, measurement of the Z. So, now you can able to see that if we go back here, A is the distance from fixed end to the force. So, for this case the distance A is this one, and which is also equal to total length L1 plus L2, and we want the displacement at the same position where the force is acting. So, Z is defining the position where we want the displacement, A is the position of the force. So, both are same here L, total L. So, if we in the previous expression of y here, if we put Z is equal to L, A is equal to L, we will get the displacement at free end. So, this is the expression for that, and that will give us, if we divide by F1 that particular displacement, we will get the influence coefficient F alpha 11. So, similarly, if we want the displacement the alpha 22, in this particular case we will be having F2 is here. So, you can able to see that basically A distance was this, which is L1, and Z is also at L1, because we want the displacement at the same position where the force is there. And so, same expression which was earlier there, this will be used. Now, in place of Z we need to keep L1, and in place of A we need to keep L2. That means, L1 position, this is the force location. So, at both A and Z we have L1 L1. So, in the previous expression, if we will get the alpha 22 expression. Now, this is the third one, in which we have force at 1, but displacement at 2. So, in this particular case we have force at 1 F1, but displacement we want at the 2. So, that means, the force location is A, which is equal to total L, but Z position is this one, which is equal to L1. So, you can able to see A is equal to L1 plus L2 total length, and but displacement we want at the second position, displacement second position. So, Z should be equal to L1. So, if we substitute this in the previous expression, we will get this expression. So, basically we are using this equation all the time in this particular case. So, this particular case we will get the expression this particular influence coefficient. Similarly, this can be obtained if we are applying the force at 2 and measuring the displacement at y. A will be L1 and Z will be total length of the shaft, and that will give the same expression of this. So, now you can able to see this from basic formula of this, we have obtained the influence coefficient for of the 2 mass system, but it can be extended for n mass system also, and this can be tabulated also. So, whatever we have done for alpha 1 we have the position of the force, second force is not there, and this is alpha 1 we can able to calculate. So, this is nothing but this more systematic way what we have explained I have summarized here. So, this is for alpha 2, this for alpha 1. So, these influence coefficients can be obtained using this. So, now once we have these influence coefficient, we can able to formulate the the eigenvalue problem. In this we have not considered the ID. So, this will take this form, and because this is a homogeneous equation, the determinant of this will give us the characteristic equation, the frequency equation of this form, and these we can able to substitute. So, we will get this polynomial. From there we can able to get the 2 natural frequency of the system. Now, we can able to see there was 2 rotor system, only linear displacement we considered. So, we got 2 natural frequency here. If we could have considered the tilting motion also, then we expect 4 natural frequency out of this system. This is the relative displacement for the first mode and second mode. So, this is the first this is the free end. So, this is the displacement of the 2 disc, first disc, second disc. Similarly, this 2 disc, you can able to see the first mode, both the disc are having synchronous motion, but in this they have anti-synchronous motion, because this is in the negative side. So, today we have seen the influence coefficient method. This method we can able to apply for multi-rotor system through simple example of 1 rotor, 1 disc and 2 disc case. We have illustrated the method, but this method can be extended for more number of discs, and even the calculation of the influence coefficient can be done using tabular method, in which by just choosing the variable where the force is acting and where the displacement to be measured, we can able to calculate the influence coefficients quite easily. And in this particular case, in the example, we have seen that even a single disc rotor can have 2 natural frequency, because in transverse vibration we have linear motion and the angular motion. In the second example, we consider only the linear motion. That is why for 2 mass rotor system we got 2 natural frequency, but if we incorporate the tilting of the discs also, then we will see that we expect whatever the homogeneous equation we wrote will be having 4/4 size, and we expect 4 natural frequency or 4 critical speed out of this. In this particular case, we have not considered the gyroscopic moment, but that can also be included. Only change will be in the moment equation, because gyroscopic moment generally affects the moment equation. So, that we are not considering in this method, but in the subsequent methods like transfer matrix method and finite element method, which are more powerful, we will be considering the gyroscopic effect also.